All right, let's get into it. First of all, welcome to the Group 712 Software Architecture and Design Team Project presentation. In 10 minutes, we've got a lot of information to cover, and you'll notice that there's a lot of information within each of the four subsections that we're going to be covering. Most specifically, we're going to give you the software demonstration to let you kind of see how that works, what the look and feel is like. Second, we'll go into design modifications and then dive into team implementation and finally go over how we not only kept track of customer requirements but also meeting those. All right, so let's go ahead and jump into the actual simulation itself. Welcome to the Osmowsis simulation. You'll notice here we have this running in a Chrome browser. And you'll see that we have 6 lawn squares represented. You'll notice that there's a gopher hanging out here. You've got 2 different mowers. You also have a charging pad, which is represented in the legend by this bluish or purple long rectangle. And remember, in the assignment, it says that each robot mower actually gets one of these charging squares so that it can recharge its energy units. In the summary section up here, you'll notice that we have stats as we go through this discrete simulation. For example, the next polled item would be lawnmower M0. We also have information about the lawn captured here, which says that there's 6 squares. Notice we've got 2 mowed squares, grass squares remaining, and completed turns. If we go down to the bottom, you'll notice that we have 3 different buttons. The stop button tends to go hand in hand with the next button. Stop allows us that as we go through the discrete simulation pressing the next button, which goes one basic turn, we can actually stop at any time and be able to get an output file partially through the simulation itself. But let's go ahead and display how next works. If we press next, you'll notice here that this lawnmower changes its orientation to the right. And as we continue to press next, now the mower has moved over here. Uh-oh, looks like the gopher has presented himself up in the top left-hand corner. Now this mower has gone ahead and cut an uncut square of grass. He's going ahead and looking ahead here so he can try to get the next one. Lawn square, and he's mowed that, and he's got to watch out for the gopher. He's hiding out right over just to the left, and there we go. So you'll notice that once we've nexted our way through this simulation, if we want to see the simulation step by step, you get this icon that appears at the bottom and it says simulation complete. You can go ahead and download an output file of the simulation run. So let's go ahead and do that by clicking here and then opening this text file, and you'll notice that we get very similar outputs to how we did with the individual implementation, but it's nice because here we are in a GUI environment. We can click on this and be able to get that output. The other capability that I want to demonstrate just by pressing reset to start the demonstration over, say you wanted to test several scenario files but you didn't want to press next to go through it and you wanted to just get there very quickly. Well, that's where the fast forward button comes in down here. If I press fast forward, you'll notice everything happens literally in the blink of an eye. I still get the simulation complete notification, and if I open this up, I get the same output. So this would allow graders or end users, anybody, to be able to evaluate a lot of different scenario files and be able to show what sort of output it gets. So that completes the demonstration for the actual application running. About the design summary discussion, things that we did as a team to be able to come up with a unified approach that would allow us to create the application that you just saw, as well as an overview of the team collaboration leading to the unified architecture of the class model, and then UML diagrams presentation portion. So you'll notice here that we've got about 5 different UML class models that each of us team members created individually. You'll also notice that in order to be able to get to an application that we could work with, not only did we need a class diagram that we could all agree upon based on these 5, borrowing from the good aspects of each model, but also agreeing on a tech stack that would meet the class diagram as well as all the customer requirements. Additionally, we had to discuss creating software contracts and work towards implementing that unified design. And in order to implement it, we used an agile approach, which we all have found successful in our careers. So here is the representation of our class model that basically takes all those good aspects of our individual class models that we proposed. And you'll notice that there are several classes here, including a gopher, lawn, and lawn square class. There's a main mower class, a simulation run class, and then also we had to add the mower communication exchange class, which allowed the robotic mowers to be able to collaborate with each other, which was a system requirement. Additionally, we created an abstract class called a mower optimal strategy, and that allows child classes of mower random move strategy and mower optimal strategy to be implemented depending on which kind of strategy the user wants to choose. Additionally, we included an enumeration class for being able to take care of direction and a status class. So let's dive in also into the team implementation section, and you'll notice here what we're going to be doing is reviewing the tech stack diagram and the team approach, covering specific design improvements that we show through those architecture diagrams themselves. So let's take a look at that. You'll notice first that we've got a deployment diagram, and this illustrates the classic client-server relationship where on the left-hand side you've got the client, on the right-hand side you've got the server. And on the client side, they're working on a web browser from maybe a PC or a laptop using some sort of an operating system like Windows, Mac OS, or Linux. And then in the execution environment, we used a combination of React and JavaScript to create the user interface experience for the client. Over on the right-hand side, you've got the web server itself, and it's running on some sort of an operating system like Linux, for example. And then in the execution environment, that's where we really get into the meat and potatoes of what we design, including the Java components from the class model that we just described, components like Pojo and Spring to be able to make that back end and the REST interface be able to transmit data over to the browser. Here's another perspective of that, of the tech stack where you have a REST-based backend. You'll notice that the Java source files conform to this class diagram that we all agreed upon. Over in the lower left-hand corner, you've got all the aspects or the artifacts containing the user interface, including the interface images that create the elements of the user interface itself, as well as a lot of JavaScript that our team developers put together. Here you'll notice that we've got a use case model for our application where we have two actors. You've got one, the end user over on the left-hand side, and then you've got a system actor, which is the simulation itself. Over in here there's several ovals that are representing individual use cases within our model, including the drag and drop a file, which includes the verify file format, and then the show file error can be extended if the person puts in a scenario file that doesn't conform to the layout that we need to make our discrete simulation run. You'll also notice that the next use case oval drives a lot of the information in the back, including the file factory to be able to input the data, and then you're going to have the implementation of getting the mowers, the lawn, the gopher, as well as next can directly include generating a report, as can stop and fast forward indirectly, because essentially what fast forward does is it's next several times all the way through the file, which drives generating the report, which you saw in the demonstration, which is merely an output file in text format. So this gives you another perspective of our architecture and things that we thought about as a team to get to our final application. Now let's dive into the sequence diagram for our application. Here this is really useful because now you're going to get to see how the individual methods within classes end up working together to create a working application based on the interrelationship between simulation run, gopher, lawn, lawn square, and mower classes. And this will drive from the top down, and the use of these methods makes the application run like it should. Now finally, let's get into the meeting customer requirements portion of the presentation. We noticed that between assignments 2, 3, 4, and 7, there were a lot of customer requirements that we had to meet. So what we ended up doing is creating a spreadsheet that uses a smart numbering system, you'll notice that each requirement number has this smart numbering of like A21, for example. So what that would mean is that would be the first customer requirement in the second assignment. You'll also notice that the requirement complete, that enabled us as a quality assurance check towards the end to go through and see if we met those, and also to make it easier for the graders to see that we've paid attention to every single requirement that happened. Additionally, we recorded what are called OBE requirements, which would be requirements that are no longer valid for the final assignment, but we included them anyway. Those would be ones that involved requirements around a crater, for example. Well, you don't have craters in the final application, so those specific requirements from assignment 2 are OBE. And as I scroll down, you'll see that there's more and more requirements where you have descriptions and then a status that each of our quality assurance specialists work to meet. And that finally leads down in the smart numbering requirement system down to requirement A726. So that gives you an idea of the requirements matrix. We paid very close attention to meeting customer requirements and treated this just like any other engineering project that we might have taken on in our professional lives. Thanks for listening. This concludes the presentation.